Good afternoon, everyone. Am I audible? Okay. So, the second session again, we are looking at another application of remote sensing based data. Okay. So, we are going one step further now. We got the, let's say, soil moisture data, or we get some other, derived indices like NDVI or all those things. What is the next level of application we can think of? So, in this study, we are looking at drought monitoring. Okay, that means whether drought conditions exist in a region, and if they exist, what is their severity? Are they lesser over a particular patch of the region compared to another patch, or are they same across the space? Those things we want to study. Okay, so in this particular application of remote sensing and GIS go hand in hand, because if we want to prepare spatially the data sets, analyze them, we need to take help of a platform where we can visualize these things, isn't it? So we have extensive use of both remote sensing and GIS data sets. So small outline would be about introduction, objectives, methodology, results, and future scope. So I hope you are all familiar about the topic of drought. So drought is the opposite of flooded condition, isn't it? We are facing shortage of water. So shortage of water, it can manifest in many ways. For example, we see that rains are not sufficient. We have received below normal rainfall in a particular year. That is our first indication that we are going to face a drought, isn't it? So therefore, we call such drought as meteorological, that is driven by the deficit of rainfall. If we have severe or deficit is like uh, departure from the normal or average annual rainfall, it is significantly deviating from the normal values, then we have to categorize that as a drought year, and that is meteorological drought. Second one is hydrological drought. So hydrological drought means the drought starts finding its way to our hydrological systems, like we don't see reservoir water levels as usual, they are below normal levels, or we don't see the discharge in the rivers as the usual values, they are very lower in the lower side. So those things are referring to our hydrological components where water is not as it is used to be. So those are related to hydrological droughts. Now agricultural drought. So agricultural drought means agricultural systems are facing the shortage. So where do we see it first? In which variable do we see possibility of an agricultural drought? Yeah, moisture content. So moisture content in the soil is the first signal that drought has started, maybe due to rainfall deficit, and now it has gone into our soil moisture status also. There also water content is lower than the expected levels. And the last one is socio-economic. Socio-economic drought means the drought situation starts affecting the progress or development or activities of the society. That means it can be result of absence of or like what you call inadequate water supply. It can be due to loss of crop yields, as a result price rise, as a result some kind of economic status also faces difficulty. So then we call it socio-economic drought. So these are major drought categories. Okay. Now every drought has a variable to associate with. If I want to study meteorology, I will go to rainfall. If I want to study hydrological drought, I will go to stream flow or reservoir water level, like that. So I can find that there is an indicator which will help me to identify. Now that indicator variable should be translated to something that is positive means good, negative means bad, or higher value means good, lower value means poor, like that, right? So I want to now make it something like an index. So for each of these drought, we also create something like an index. An index means it will tell us relatively higher or lower means drought has occurred or less severe drought has occurred, like that. So meteorological drought will have a drought index which uses rainfall. Agricultural drought index will have a index that uses soil moisture in some way. So like that, each of these drought can be studied with the help of certain variables. They can be used to develop some indices. These indices can be categorized. So some values may be looking at the extreme range, which means extreme situations. Some cutoff can be there which tells us the difference between a normal condition and a abnormally dry or abnormally wet condition. So there are categories for drought indices which will help us to study drought. Okay, so this is the basic idea about drought. And monitoring drought means we are looking at the condition on the ground or condition of the area to understand when it will start, like when is the onset of a drought event, when it will end, the termination point of a drought event, and in between this, what was the duration, maybe in months, maybe in weeks, and in that duration, how much is the total magnitude of severity. So something like we use the index to calculate these kind of quantities. So if I can find out the index time series, then I have a monitoring in place. So that monitoring, then I can assess, okay, the drought started here, ended here. This is more severe event than the past month's drought, like that. I will be able to compare across different locations also if I have different data. I have long-term data means I can say whether this kind of drought is becoming more severe with time or they are becoming lesser in number or more frequent. So all these things are derived from monitoring exercise. We get a lot of information once we start monitoring the drought events. So our motivation for this particular research was that agricultural drought monitoring is a challenging problem, because what will tell you exactly the drought has started in an agricultural area or field is something people have different versions. People like to also study evapotranspiration to understand drought. People like to study rainfall also to understand agricultural droughts. So what is the best way? There is some kind of, always a multiple opinion about that. So there is no one solution like that. People take different factors into account. People have multiple indices to look at. Then they decide that, okay, all of them agree that there is a drought is there. Like that also it's possible, not depending on single variable, but multiple factors. So we also took such an approach. So don't rely on one variable or one indicator. Why don't we rely on few extra indicators? So that kind of an integration we wanted to do. So different drought indicators, some of them suggest what is the health condition of the plant or crop. Some of them can suggest the stress affected on the plant. Some of them can monitor the soil moisture and then find out what is the deficit. So in that way, a multiple approach was followed. And then we can see whether this particular framework will have some added advantage. For example, can it tell us in advance early warning? Or can it tell us very precisely that the drought events are of this much duration, or it is likely to be there in this month? like that, or this particular region of the study area is more prone compared to another, like that. Okay. So therefore, the objective of this research is to develop a framework for agricultural drought monitoring using remote sensing based data, and that will utilize multiple indicators such as something representing health of vegetation, crop stress, and soil moisture level for the monitoring purpose. Okay, so that our data sets we are not able to measure, so we are depending on remote sensing, and we are going to integrate them and then study the drought. So in this particular case, we looked at the whole state of Odisha as our study area. That means we wanted to study all over Odisha what is the general pattern of drought. So here some additional information was like irrigation facilities and then cropped area, that is just to supplement the pattern of agriculture in the state. And here you will see a very exhaustive list of data that was used in the research. That means we started from a long list, because which one is a good data set, which one is the best data set, nobody has an answer, right? So we started with a very long list. What are the possible data available for land surface temperature? What are the possible data for surface inductance? What are the possible data for surface soil moisture? And then rainfall. All these things we wanted to look at. For rainfall, it was quite very narrow, because we don't have other than IMD, such a very vast network is impossible. So IMD data we have taken for rainfall. But remaining, if you see, like land surface temperature, there are data coming from satellite missions, like MODIS data is there. Then there are satellite plus model. There are some land surface models like GLDAS, FLDAS. They also provide temperature data set like this. So that source of data name has the keyword GLDAS, NOH, FLDAS, NOH, like that. So those are different missions or different projects handled by different world organizations, countries. Different countries are competing in kind of advancing the science, right? So they have different models, different resolutions also, like 0.5 degree, 1 degree. They are all giving this data, but nobody can claim mine is best until we validate with our study area, like that. Similarly, surface reflectance also we can get from MODIS as well as Landsat. Because which one is good, nobody knows. One may be good, one may be okay, like that. Then for soil moisture also, we didn't develop anything fresh from any data set, because it's for all over Odisha. Nobody has that much field data to validate. So we existing data sources like coming from AMSR, GLDAS, FLDAS, and India WRIS WIC model. We used this kind of freely available data. Okay. Now we are going to have multiple indicators which will give us vegetation condition, crop water stress, soil moisture, etc. So they are the ingredients that go into it. Okay. Our next step is to select best among these and construct those predictors. Right. Which climate index? They are different variables. For them, we need sea surface temperatures. So they are not available in these names, but they will be there from different sources. So what is the schematic? This study, we start with the basic data like temperature, rainfall, vegetation stress, soil moisture, and some yield information about the crops, because we want to do some validation whether some year was drought or not. So all these data will be pre-processed. That means either they make everything to IMD gridded or 1 kilometer gridded or something like that, depending on our requirement, isn't it? Now, once we have all this data in place, we need to create the agricultural drought index. And that drought index will do the monitoring for us. Okay. So, this agricultural drought index will be made up of different indicators. And this agricultural drought monitor or index will be used for drought monitoring. And when we say drought monitoring, we also want to improve that system to give some forecasting capability. Can it forecast 1 month ahead? Can it forecast 2 months ahead? We also want to identify drought hotspots, whether one particular part of the region is more vulnerable than the other, whether it has faced more number of droughts compared to another part. So these things we want to do spatially also analyze them. So we will start with indices like this. Yeah, I'm elaborating it here. Yeah. So like we have seen, we want to monitor vegetation health, so crop water stress as well as soil moisture. One by one, we can see what are our choices. Okay. So here the first condition was vegetation health. We want to monitor that. So in the previous talk, we have become familiar with indices like these, right? So NDWI. Then there are similar indices like vegetation condition index VCI, temperature condition index TCI. So you can see they are all some are optical bands. VCI is made up of NDVI. Then TCI is made up of land surface temperature. So if I have many data sets giving land surface temperature like I showed in the previous table, I will choose one of them which is matching with observed temperature very well. So that particular data only I will choose to calculate TCI. So that way the first list of data was used to select the best one and then used to calculate TCI. Then NDVI and all we can use the brightness, temperature or data from surface reflectance, which one is good like that we can choose. So that way this index representing vegetation health, we have 3 choices. Okay. Next one is crop water stress. So from literature we found that there are some indices which are good at representing the crop water stress. So we don't have a first hand data of how stressed a plant is. We are not measuring it using any instrument. So we have to rely on previous literature or previous studies. So people have found that this SIWSI index is good for that. Okay, so they have SIWSI1 and 2 and this row represents the band only. So earlier we saw that Sentinel names them B1, B2 like that. Now in other cases they name it like generally with a symbol row. So row 1, row 2 like that, there are many numbers. So here you can see row 2 means the NIR band, then row 6 means the SWIR. Similarly, row 5 means SWIR, another wavelength range. So like that, these addition and subtraction, we have seen in NDVI some similar equation, right? So similarly, they have used another equation for SIWSI. So these are the popular indices good for representing crop water stress as per previous literature. Now similarly, we want some indices that can represent soil moisture status. Okay. So in this particular study, we used 3 candidates: SMCI, soil moisture condition index, then SMDI, soil moisture deficit index, SWDI, soil water deficit index. So you can see their formulas are different because different scientists have proposed these based on their data or their experience with the field observations. So in all these cases, data coming from soil moisture has been used. Those different symbols are used. You can say that most like combination of soil moisture data is being used, minimum, maximum, relative to that, where do a particular time period's moisture stand relative to minimum and maximum. Okay. So that can also be calculated for soil moisture based indicator. Now I have few indicators. I have to choose which one should be selected from each category. Okay. So for that we did an intermediate correction or check with the help of yield data. So we checked whether indices correlation with yield is higher or lower in certain cases. So ideally that means out of the 3 in this first, one of them would be better correlated in that particular location. We go for that one as the indicator for the vegetation health. In the second case, for crop water stress also, which one is better correlated with yield? That one we have chosen as the representative from crop stress. Then the third one from soil moisture level. Here also one of them will be more correlated compared to the other in that particular area. That one was selected. So the selection of one from each was taken. Now, once we need to club them to get our final indicator or index. Okay. So the combined drought index in this particular proposed methodology has indices multiplied by their corresponding weights. And to determine the weights in this particular case, we used a weighted entropy approach. So weighted entropy approach means depending on the data, that means I have three indicators now. The contribution of these 3 indicators towards the final index would be dependent on how much variability is there in each indicator. So it's a mathematical analysis. It requires extensive, discussion about its own what is behind it. So I'm not going into detail. It's just like we did a regression. Think about that way. When you did regression, what did you have? You had some weights assigned for each of the components. So here also each indicator requires some weightage. But this is not a regression problem. This is a weight determination problem. So we determine the weight based on how variable each indicator has been and likely to affect the output. That means our index. So therefore, the equations are based on the ranking or the relative, entropy of each of these input variables. And then finally, with the help of equations, some weight can be calculated. And you can determine weight based on multiple approaches. Some people assign equal weights. That means that if there are 3 variables, each would have weight of 1/3. Okay, equal weightage for all the variables. Some would want to check the correlation and say that, okay, this is correlated to the yield more, so I will assign more weight to that one. This is less correlated, so least weight to this one. Like that also is possible. Here we did some methodically, we went for a approach that is entropy based. That is the thing. Now, once we have this drought index, the value ranged from 0 to 20, like that, sorry, not 20, 0 to 1. Okay, the value of our index range from 0 to 1. Now we need to classify them into categories, because every index is best understood if you put them into a bin category. That instead of saying, oh, my index says value is -2, nobody understands what is -2. But if you put minus to a category, that okay, this means extreme, -1.5 means moderate, something like that, people will understand better. So for that, we have to categorize into certain categories like abnormally dry, moderate dry, severe dry, like that. And for classifying that, we take the range and divide it into percentiles. So that means effectively, if you have 0 to 1 as your limit for the entire drought index, then less than 20 percentile of that range would mean a drought situation. Above that, it is no drought situation, like that. So here also some similar classification was made. So abnormally dry is 20 to 30. Above 30, it is good. I mean, wet condition, no need of drought. Below that, we have categorized as different ranges. So if our index has a value of 0.2, we know that it is in the borderline of being a drought situation. If the value goes back to 0.05, we know that it is in an extremely extreme situation, like that, percentiles. Now, this is the different indicators, how they looked when we calculated them. So you can see SIW, SI1 and SIW, SI2, they were used for referring to crop water stress, isn't it? So their time series of all the locations or all the grid locations of Odisha were plotted together, and you can see there is like, when it was slow for most of the locations. So something like a drought condition, non-drought condition kind of comparison. So each index can tell you that it is stressed, not so stressed, like that. Locations, grid locations. So Odisha is divided into 18 locations. Each location has a time series plot from 2001 to 2020. Yeah, grid of, not satellite data, all the data of we have used remote sensing also. We have used land surface model also. So in that, we have taken one scale. So according to that, Orissa had 18 grids. 18 grids, yes, as per the data's resolution. So some data were very high resolution, some were very coarse. So finally, we had to look at the coarse part. So and that is why only 18 grids for entire Odisha. Okay. So here are some of the areas where there were significant understanding about drought years. These were some of the drought years, and we have seen that there are values in the drought condition range that agrees mutually also, as well as with the record of the disaster management authority. So that is only validation we could do. Means government also recognizes these years were drought years, and they have been picked also by the index. There are also other years which have been suggested, but in records it's not drought. Similarly, for soil moisture, how these indices would look like if they were plotted in a time series. So here also some of the drought years. So in this case, the drought years are in the lower side, down part. Okay. So now once we put the weights, we estimate the weights and then calculate the index. The combined drought index can also be plotted for all these 18 locations. So that is the 18 locations and 2001 to 2020 time series of combined drought index. So here also you can see the values are going below 0.2. When the values are going below 0.2, it is a drought condition. When they are above, it is a non-drought condition. Yeah, so below 0.15 or 0.2 something, drought is supposed to. Those were individual indicators. This is the combined index. So it combines information from across three indicators, then calculates and assigns a category to a drought. Okay. So you can see which all indices we found to be useful. So from soil moisture status, SMCI, from the first one that is for vegetation health, TCI, then from the crop water stress, SIWSI 1. These were selected as per the analysis and their weights were determined. And weights were different for different location. That's why we cannot put any one number. Each grid had its own weightage for different index. Now, this is the spatial analysis for which we can use GIS, or we can also use any programming languages to perform such mapping and all those analysis. So here we have calculated some drought hotspots based on average annual drought severity and average annual drought duration, and that is based on the CDI, that is the index we have proposed. So we find that there are some regions which are more affected in terms of severity compared to the rest of the Odisha. So if the value of the drought severity is on the lower side, then we see that they are affected more significantly. If the drought duration is more, they are also affected more critically. But this is a very coarse resolution result, so we cannot rely on that to be more accurate. Then again here, total duration of drought months and total duration of extreme or severe type of drought months. So that also was plotted. So if we see that the variation between other areas and the critical areas are in terms of maybe 3 or 4 months. So drought duration lasting for 4 months and drought duration extra lasting for extra 4 months would, but that's the only difference we see in this course as analysis. Then similarly, drought hotspot maps. So here what we did for the whole Odisha for the entire 20-30 years like that, right? Now we are looking seasonally. That means for Kharif season, for Rabi season, whether this pattern is uniform or changing. So in the images that you can see, Kharif season, then Rabi season and the summer season. So we see that the severity is calculated as here number of months in drought. Okay. So more the number of months in drought, then that would indicate more vulnerability is more for such regions. So consistently what we saw is that the southern part had more proneness for vulnerability. compared to the northern or coastal part of the east. Now, so we have seen the results. So there is a lot of scope here for extending the work. That means once we had the limitation of data being very coarse, then there were so many data to look at. So a lot of energy was spent on which was the best data. If we had more detailed yield information, things could have been more good. But our yield information is limited to districts. We don't get any grid-wise yield data or anything, right? We have to rely on district level data. So in that way, our analysis would have been better if more high resolution data were available. Not prediction, but early warning. Yeah. If our index can predict the, or if the index can be predicted with rainfall data, that kind of analysis. Little bit investigation be carried out, but it is not very high performance in that. So we see that this particular framework can be adopted and applied for more higher resolution data, so that instead of getting 18 pixels over Odisha, you may get 1800 pixels, like that. So more higher resolution data is desirable. Then we can use this combination of the indicators. Here we have discarded some indicators, but if instead of discarding those indicators, if we could reduce their dimension and still extract some useful data. So for example, we can use dimensionality reduction techniques like PCA, or things like orthogonal factor analysis or something like that. It may lead to a better estimate. Then further work is also like, what is the scope for early warning? That means, can you tell today that an agricultural drought may come in the next 15 days? So some early warning if we can give. That means if the rainfall analysis or some other current condition in the field can suggest that the combined drought index will point to a drought situation 1 or 2 weeks or 1 month ahead, then that would be a very good value addition. So these are the work that we want to extend this kind of framework to. That means find out better data or more reliable data to validate also. It means we want validation for everything to prove that the framework is good, framework has some scope, like that. So that is the future scope of this particular research. So that's all from this session. So if you have any questions. Okay. So if you want to project the drought for next 10-20 years, satellites are out of question. No, nothing can come from satellites. But what you can use is climate models, general circulation models, GCMs, RCMs. They are able to give us some kind of estimate of the rainfall, or they are also even able to give some kind of estimate related to maybe not soil moisture, but maybe something related to ET, or which you can calculate ET based on that. So you can indirectly get an idea. So rainfall based droughts very easy because rainfall is available. You just have to downscale, correct it to the local scale. The other ones you may have to do some indirect analysis. Yes, yes. Yeah. So only rainfall you can get. but you can run it in a hydrological model and get the soil moisture. That is possible. That means we take some variables, run the hydrological model, get the other variable, use it for drought. That is possible. Any other? So PCA tells you that okay, you have, let's say, n data variables, but you cannot put n numbers in the calculation because it will require so much effort and convergence and everything. But let us say if there is a way to get some pooling of these n things into multiple, what you call, dimensionality reduction by putting them in some kind of coordinates, just like that you can think of, or putting them into some kind of derived things. So each of those derived direction would be a weighted combination of some of these n. So from n you may have the facility to choose 3 or 4 even, or 2 best what you call derived angle, or some kind of combinations that are capturing the essence of these. So those are the weighted kind of so we use eigen matrices and all those things to calculate that, and we are able to get from n to 2 or 3, but they are made up of those n, and those with the least importance will have automatically the least weightage, etc. So we will find that even if we add them or discard them, that will not affect the results. Predicting. Yes. They don't help in predicting, but they help in telling us that this index is higher in certain times of the year, lower in certain times of the year. So, and in this range it can fall. So we get to prepare ourselves looking at the condition, current condition. Okay, I know that I should expect this severity of any in the drought, or in this time of the year it is more likely to affect entire state. So such things we can get from that kind of analysis. For if we want to predict, we have to build entirely different framework that would have to extend this kind of research further. Mm. Yeah. PCA copula can be applied on any data set, but in this particular application, if we were to apply PCA, that would be like, sorry. So in place of this W1 into index 1 plus W2, I would be telling that, okay, index 1 would not be after eliminating other indices, but I can add all of them in the combination and still get a weighted indicator like that. That would be a separate analysis. If we are looking at how many variables, how many, how many principal components we want to choose, depending on that. Yes. Sometimes 2 principal components are enough.